I'm going to take you through a run through of a MIRISim notebook. If you want to code along, the version of the notebook you can see here is MIRISim MRS Walkthrough Webinar. If you want, there's another one with a longer name. That's the fully complete notebook with everything rendered. So if you just want to follow and not run the cells, or don't want to bother typing, you can restart that notebook from scratch and enter the cells as I do, taking you through the walkthrough. The notebook I'm going to talk you through is an MRS simulation. In most instances, between the MRS, the low res, which is the IFU, the imager, and the low resolution spectrograph, many steps of the notebook are the same. There's just one stage which is slightly different. Within this notebook, I am going to spend a lot of time talking you through the process of manually how you would create your science scene, and then setting up the simulation parameters. We will run the simulation, which in this case is quite a quick simulation, and then quickly examine some of the outputs. Throughout the notebook, if you do have any questions as we go, please ask me. And I've also included within the notebook useful functions at the bottom if you wanted to use a FITS file or an APT, but I'm not going to discuss them today. And also a table of content and listed resources for you to go backwards, so that hopefully this notebook will be a catch-all tutorial. If I do miss anything or we run out of time on discussion, the notebook will reflect the wide parameters of stuff that MIRISim can do. There is also handily an installation check, so if you're not running the MIRISim on the system, but on your own computers in a Conda environment, just some help on how you run a notebook from the terminal, and make sure you activate your MIRISim environment before you do that, otherwise errors will occur. But that's just a way to check as well. So starting off, in terms of our simulation, in the first cell, import your normal basic Python parameters, for instance numpy, matplotlib, and just a nice way to display the wider field of view of your notebook. So now the next set of imports are more important. These are the MIRISim specific packages. There are three main components from MIRISim: the config parser. So that includes your simulation configuration files, your simulator configuration file, and your scene configuration files. And then, depending on how you want to set up your scene, you want to include a background always. If you want to deal with your own spectral energy distributions and add them to an object, you will need to import that from MIRISim. If we're dealing with point sources, you want to import points and extended sources, or dealing with kinetics, or import your own external spectral energy distribution from a file. There are other components you want to import from your MIRISim specific packages. They're ones I typically import always. The row below is if you want to ever use any of the models from PySymphot, which is part of the synthetic photometry package in AstroPy. You can use the models there as well, but I don't always do that because many of those models are not suitable for the mid-infrared. So be very careful if using those models. Make sure you check first what wavelengths they cover. And then finally, the final stage of key imports for MIRI is the MIRI simulation import. And just as we're going along, I've kept the timer so you have an idea of how long a simulation will run. So the very important part of MIRISim is creating a scene. I'm not going to go through the background level information on here, but there's two key things that you need to do always, which include a background level and a science source in any scene you generate. There's information here on various different types of scenes you can make and different types of objects. It's very powerful and very versatile, but I've just included that information for your future knowledge and questions. So if you want to build a scene, in this case we're not going to use a FITS image. This is actually building all the components individually. And the very first thing I always do without fail is to import a background. And the background is the telescope background, but also the sky background as well, of what you'll encounter in your image. And so I imagine name this background, my background level. The level can be low or high. And you can include a gradient across the image for your background if you wish, and also you can change the position angle. So let's have a play around from the default parameters. If you are coding along with this, feel free to alter parameters as you go to see how and experiment with MIRISim. So that's the very first stage I tend to always do if I'm building a scene from scratch, is to make sure I have a background level. So yeah, if you're coding along with me, we're going to start making point sources now. Whenever you add an object to the scene, which is not the background, there are a couple of things that you always need to do to the object. First, you need to give it a location on your detector, and then the next thing you need to do is add a spectral energy distribution to that object. They are the two fundamental things that always has to be done to any object. In the first instance, we are going to happily make a point source, as this is the very simplest object you can do. And you do any point sources you want to make with MIRISim, you use point, which we've imported earlier. And the next thing to do is give it a location within your detector. We do not in MIRISim use RA index or coordinates. It's all relation to the center of the detector. So if you want to give it a position, here I've added center equals, and in this case, the center of the detector is at 0, 0. So my point source I'm adding here is 0.5 to left, and then it's slightly up. So this is your x coordinates and this is your y coordinates in respect to the detector. The next thing you want to do after you've said your position is to add in a spectral energy distribution. In this instance, the very simplest case is to take a black body to attach to the point source. So you want to set properties of SEDs. You can there is many parameters you can use, including power laws or reading in your own SED properties. And to do this, you use the SED class within Python and MIRISim, and you can then nicely have your SED, and then your list of options can be available using autocomplete if you have not used this before, by pressing the tab key. So here I want to use a black body spectral energy distribution, and to set your properties here, you need to know the temperature of your black body. In this instance, our black body is going to be moderately warm at 800 Kelvin. So the black body is in Kelvin. Then you need to give a reference wavelength in microns to where you want to normalize the black body flux to. So here, this is set by JWref and then 10 microns. And the final thing you want to do in initializing a spectral energy distribution is to give it a flux. And the flux here is in micro Jansky. So the body will be at an 800 Kelvin black body normalized to 1 × 10 to the 5 micro Janskys at 10 microns. After you have done that, we have our point 1. You want to set your spectral energy distribution by adding it to the point source. So you can do this by typing set SED, and then now we have our SED of our black body. We have added it to the point source. And if you don't believe me, nicely within MIRISim as a function, without having to do any other plotting parameters, you can type plot SED. Okay, we're not going to see that SED. For now, you can see it in the rendered notebook instead. Just to give you another example of what you can do, I've now made, I'm not going to talk you through everything again, I've made a second point source 2. Here I've added actually a model from the Python PY spectral axes. There's the documentation of the models, and you need quite a lot of dictionary work for this. So be very careful. The documentation is linked to at the top. Again, this is where we have imported the dictionary parameters, and you add a second spectral energy distribution by using set SED and then your second parameter. And what I wanted to just show you here is now when I really do actually plot the spectra is the point about being very careful if you want to use library models, because compared to a black body, there is actually only a few points where a model may be sampled. So it may not be optimized for the mid-infrared where MIRISim operates. So I've now created 2 point sources, one with a black body SED and one with a model from the libraries available from PYSimplot. Point sources are all well and good, but I know many of you are actually interested in more extended objects. And one of the ways to add an extended object, in this instance a galaxy, is by using the galaxy class. So while in MIRISim it's called galaxy, it doesn't necessarily mean it is just a galaxy. It can cover any range of spectral energy distributions, any range of extended object shapes, and there's quite a lot of powerful tools you can do to each of these objects. There is also disk objects you can use to make an extended source, but I find galaxy works in almost all instances of science. As before, I want to give it a location. So the first thing you do is always set the properties of your object, the spatial properties. So I have given it a location. At this time I'm right in the center of my detector, and then I want to give it a Cirsic index. So here n equals 2, and then I want to also set up the effective radius of my galaxy, my axis ratio, and also a position angle. In the interest of saving my bad typing, I will just copy and paste from the completed cell here, but we can set these parameters to, let's set the position angle to 45. RE is your effective radius in arcseconds, and Q is your axis ratio. Let's change this a bit. So we have now initialized a galaxy with some extended properties. As before, you want to add a spectral energy distribution. Before we added a body, this time we are going to add a power law for the spectral energy distribution instead. So before you use this SED class, and then instead of black body, it's a power law spectral energy distribution. You give it an alpha value for your power law, and again a flux in microjanskis, and a reference wavelength in microns. It doesn't have to be 10, just should be within the MIRI wavelength range. And then, as before, you add this spectral energy distribution to the galaxy, and you can plot the spectral energy distribution. And this time it will work because I'm not typing on the fly. So here we go. We have a very nice SED power law shape. I don't want to get too much into this now, but if you do want to have a galaxy and you want to have velocity maps, you can do that using the kinetics profile and a flat disk. You can set the rotational parameters, the center, where you want your velocity to be, your position angle, and again angle and boxiness and diskiness of your galaxy. So you can add a velocity map, and if you wanted to, you could also add a line of sight velocity distribution to the galaxy, which I've commented out here. Just to show you, again, you can plot from the object class, the galaxy. You can plot the spatial information. So I've set up a galaxy which is actually very far from spherical, but it is actually in the center of my detector in arcseconds. So again, just for as a check, I've set up my object correctly. You can just plot your position, your spatial information, and your spectral information. Just as an example, I want to create here another extended source. This is an example of, again, setting up in the center of the object. I'm not going to include this in the simulation, but you don't have to have a spectral energy distribution of known parameters. If you just have some spectral lines you're interested in, you can actually just model the lines themselves, or you can combine any lines with a power law SED or a black body SED to make your own more complex distribution. It's an example here. I'm not going to go into this now because in the interest of time, but there's a similar principle of set up your line strengths and your full width half maximum of the lines, and then add them to the object that you've already initialized as position using the set SED parameters. And just to give you an example of this object, I've made a different shape extended object. Still put it in the center of my field. This is normalized, but here I've just added 6, so flat spectrum with six lines at specific wavelengths of a known flux, an integrated flux, and that's in 10 to the minus 20 watts per meter squared. So just be very careful of units while initializing any lines. But I just want to give you an idea, it's very powerful. You can also import your own spectral energy distribution as well. So once you've made your different components, you actually want to put them all together into a scene. And MIRISim can be versatile here. For the first scene, we have made a few objects. I want to here include the background, my point source 1, my point source 2, and the first galaxy I made, not the extended source above. The way you add, so you make your individual components, then you just add it together into a scene. You can also alternatively use a target list, and here, instead of just adding the components together, you make a list within Python, but don't, if you're having a target list, do not include the background, just your point sources and any extended objects within a scene. And these can both be exported to a .ini file, which can then run from the terminal later on if you so desire. The final part of any scene creation is to make your simulation, your scene configuration file. And you can do this using scene config and then make scene. The very first parameter is your log level. That's just how much information is output to the terminal or later on of your simulation. So it's just a text file of how you've set everything up and good for debugging. In this instance, I've put my background equals to the very first thing I did, which was my background. Always include that. And then my targets of a point source 1, my point source 2, or my galaxy here. If I wanted to, instead of having the write them out, I could just add targets equals target list instead. And for safety, if I want to run the simulation again and I don't want to go through the rigmarole of making a scene and sources, you can write your scene to your directory. But here I've just removed the first scene first, any other previous scenes I may have made. So that's the step where you spend most of your time in a MIRI simulation. The next thing you need to do is set up your simulation configuration. So this is where, if you have a handy APT file, you can read this in and you don't have to set it up manually. If you do want to set it up manually, this is how you would do it. There are four main components of your simulation configuration. And here I've called it handily simulation configuration. And to do this, you use simconfig makesim. And the first part includes the name of your simulation and any scene that you've already made. So here, before I save my scene as a .ini file, you can simulate the start of your when JWST is starting to observe on the sky early in the mission or later on in the mission. So by setting a number between 1 and 0. And the key thing, the difference if you want to use the imager or the LRS or the MRS is set by pop. This is the one point in your MIRISim that would differ depending on what observing mode you wish to do. So if you want to use the LRS, for instance, you would set pop to IMG, the imager, because it's in the imager plane. And then the configuration path is the light path you want to simulate for your observations. So for the MRS, there's 12 different light paths. Keep this consistent to 1 to make your simulations all overlap in parameter space. So you'll set your optical path to keep that constant throughout your simulations. So here I put the MRS 2, and then the short channel is where I'm focusing these simulations on. The next part, and I've explained in a lot more detail in the text just above this cell. The next part of the simulation is for setting up the MRS, which are this section here. If you're doing an imager simulation, these values need to be kept. They are still read in, so do not delete anything in these cells, but they are ignored by the simulator. But they need to be there. Do not delete the MRS if you're doing an imager part. And similarly at the bottom, we've got big not used here, but this is where you would set up any imager simulation parameters. So do not delete anything. Make sure you have all these lines within any simulation file, otherwise MIRISim will not run. For the MRS, you have a choice of 3 dispersers. You can run short, medium, or long dispersers. If you want to simulate the full spectrum from 5 to 28 microns, you'll need to run the simulator 3 times using both the short, medium, and long dispersers. So this is where you'll need to loop if you are going to simulate the full spectral range. For detectors, you can use the short wavelength channel, the long wavelength channel, or both. So in the shortest possible run of MIRISim, to get the full spectral range, you would here for detector use both, and then you would loop for short, medium, and long. If you just wanted some components, you can pick the specific channel you wanted. Similar to your APT file, where you pick your read mode of fast or slow, MIRISim can do that here. So the MRS mode I've chosen fast, as that's now the default. And then the number of exposures, the number of integrations, and then the number of frames. And by frames, this is equivalent to groups. So this should be equivalent to your observational setup in any APT file or any exposure time calculator. In the interest of time of the simulation run, I'm not going to dither, but if you wanted to use a dither pattern, you would set this equal to true, and you can set the number of dither points and exactly where you want to start in your dither position and whichever dither pattern you wish to use. And then finally at the bottom are some parameters set for an imager run. Again, do not delete these. Even if you're not running an imager, do not delete them, they need to be there. I cannot stress that enough. But it's a similar pattern: number of exposures, number of integrations, number of groups, your read mode, and then which filter you'd want to read. In this case, I was using a bright sky subarray as well. Could use a subarray if you wanted to. But in this simulation, none of these parameters are included. They are there, but they're ignored by the MIRISim tool. So you have set up your simulation config, which is very key. That should match your APT file. And then again, I have now written that to a file just for safekeeping in the future. Finally, there's one final step before you can run a simulation, and that is to set the simulation config. This is possibly the easiest part of MIRISim, because unless you're an absolute expert user, you just want to use a simulator configuration from default. But you can't just skip that step, it has to be always included. And then to run the simulation, I've imaginally called the simulation MIRISim, and then you need to include in your simulation, by typing MIRISimulation, you need to have your simulation config file, which I've just included above, your scene configuration file, which is your scene setup, and then your simulation config, so that's your read modes, etc. in groups. And now we have set MIRISim up and running. This simulation setup takes approximately 3 minutes if the files are downloaded from the server. If it's not downloaded, it will take a little bit longer. And the way to run your simulation after you set up MIRISim is you go MIRISim and then .run. There we go, and you'll start getting a terminal full of lots of information of the start date, end date. If there's a crash due to CDPs, this will tell you quite quickly in this information, and it tells you exactly what maybe band is being simulated. For instance, your optical path you've chosen, your point sources, your galaxy sources, if you've added any velocity. All that information is output at this stage. Maybe that has, the simulation may have ran. Oh no, it's still simulating, so it tells you where you are. It's on the first integration. Because of time, this should run in about 3 minutes unless you are downloading the files, in which case it can take much longer. I'm going to just examine some of the results. MIRISim outputs its results in a date directory. Normally, I would grab the latest simulation, but here I've pre-ran a simulation similar to this, so I'm using that output directory instead. So I can list the contents in the files and the subdirectories within here. As it's an MRS run, there are 3 sets of outputs, as Pamela mentioned: the detector image, the illumination models, and the sky cubes, and which of the detector images are the results that you want to put through the JWST pipeline. And it also tells me it's also saved my .ini files and the log as we're going along. Before there was a question about the log. So if you want to see all the gory details, depending on what log level output you put, you can read it in there in your output directory. And there's just some information to include these. I've included a useful function for showing outputs, of which I'm not going into now, but that makes my life easier if you want to view a size of your sky cube of the sky. So here, included a very, very, very elongated galaxy as my extended object, and then my point source in the sky cube. Within this is just a slice. You can change that function to look at various points within the cube. And this is the MRS field of view alpha parameter and your beta parameter at the side. And it tells you which channel, so it's the center channel set up in this particular instance. But it's handy because then you can quickly look at your illumination model as well. The problem with having a catch-all function is it may not be great for your contrast. So here, this is along the MIRI cube, along the wavelength slice. You can do this manually. Again, the information of reading in the FITS files of the illumination models with the FITS information and some stretch. If you wanted to, you can have a prettier version. So, but unfortunately, I don't have the labels here. So this is, you can see the curve of the short and long wavelength part of the detector. I think this is very cool, but very hard to interpret intuitively. This is better for your pipeline, of which you would add your final detector image. So again, using show outputs, again, along the slice direction in this axis and along the wavelength direction on the y-axis. And then the information included in the FITS header in the final detector image is exactly the information that you need for the pipeline as it currently stands. So if you include information on spacecraft pointing information, that's included in the simulation. World coordinate system parameter information is added. So and data numbers. So the pipeline has all the information needed to read in that detector image and process it as if it was observed on sky. And the final point to do, you can view your detector image manually. It's thinking, this is where I've just integrated over, instead of showing one detector image of grabbing one, I've run the simulation for 12 integrations. And again, here you can see the cosmic ray effects we've added in the stretch. I think we'll go to some of the brighter parts of the image. You can see all the noise included. I think you can see, if you look carefully, you can see fringes effects. So these are all then now the simulation components added together, ready then to be processed in the pipeline. And I think, and you have any questions, the link to the pipeline can be found there. That will be the next stage. Go to your next environment and run it through the pipeline. And just at the bottom, I've included some convenience functions for how to use the APT files, reading FITS images. And if you don't want to spend your time making lots of point sources, for instance, there's some nice functions included at the bottom to make your life easier. So I'll leave it there. Thank you very much.